I'm going to talk about how can we build a filtration on something like genuine G-spectra. And I'll just say, sort of as my slogan, that plays nicely with various twisted products. And so let me start with the warm-up. And the warm-up is G is the trivial group. Oh, and here, so I can forestall the question, G is a finite group. So when I start with G as the trivial group, well, now I'm asking, I want to build a filtration on spectra that plays nicely with just products. There's no twisting that's going to be involved. The twisting is an interplay between the group action and the coordinates as I multiply. And so the example here, in fact, the usual Postnikov tower works very well with products. But in fact, it does so in two ways that are important. So let's say that R is a -1 connected commutative ring. Then I can form its Postnikov tower, which sits under R. And I have the 0th Postnikov section. This is just some Eilenberg-MacLane thing. And then I have the whole tower that sits above it. And one of the nice features about the Postnikov tower is that, in fact, the tower itself sits in the category of commutative ring spectra. This is a tower of commutative ring spectra. And in fact, I can do better. Sort of, if I was just associative, then this would be work of, say, Shipley. And if I'm in the commutative case, then I'm looking at work of Bastera and Mandel that are telling me not only is this a tower of commutative ring spectra, but also I can think about these as square zero extensions sitting over the base. So if I want to understand what are maps into this, or how can I understand sort of an obstruction theory for lifting maps of commutative rings into, say, just the bottom piece, this Eilenberg-MacLane thing, how can I lift those up to maps of rings from something into R? There's an entire obstruction theory that's built out of these square zero extensions. That's what's often called Andre Quillen cohomology. So just looking at the Postnikov tower, I build an obstruction theory. If I were not in commutative rings, I would call this obstruction theory the Atiyah-Hirzebruch spectral sequence. And if I'm in commutative rings, I guess I could also call it the Atiyah-Hirzebruch spectral sequence. But we normally call it like topological Andre Quillen cohomology. That's giving me a way to understand maps into this via this tower. So this is the sort of thing to keep in the back of your mind, that I can understand all of this in terms of this really nice, pretty straightforward construction. But I can do better. I mean, I can't do better with the boards, like with Catherine sort of amazingly getting it to draw nice straight lines, having it move against the chalk. You'll have many opportunities to laugh as I try to move these. But the additional feature that I can do is, instead of looking at the Postnikov truncations, which is what I did on this side, I have the dual story. I have the Whitehead tower. So these are the Whitehead covers. and these sit over R, and I have the part, well, it actually starts with R, and then I have the part where I've thrown away the 0th homotopy group of R, where I've thrown away the first 2 homotopy groups of R. So in spaces, I guess this would be the path component of the, I don't know, identity, and then this of the base point. This is the universal cover, and so on. And when I say that I can do better, and why am I talking about the Whitehead cover here? This was a tower of commutative ring spectra. This instead, this is a commutative monoid in filtered spectra. So I have an obvious filtered spectrum here, where I'm thinking of it as just, say, a map from the integers op with the usual ordering into spectra. And I'm saying it's a commutative monoid. Well, the integers have an addition, and so I use the day convolution product for functors out of the integers into spectra. That endows filtered things with a symmetric monoidal operation, and I'm saying it's a commutative monoid there. This is just a fancy way of saying that if I take the kth filtered piece, p at least k, and I smash it with the lth filtered piece, then I have a multiplication that takes me to the p plus, to the k plus lth filtered piece. So it's exactly the thing we think in algebra. So I like this version because I like to think about this again from sort of a computational perspective. What am I going to be getting out of this? And here I'm saying, okay, if I'm looking at something like this and I want to compute something like the homotopy groups of this, if I'm using the Whitehead tower, then I see that I'm looking at the homotopy groups of some filtered commutative ring that's converging to my commutative ring. This is going to be a spectral sequence of algebras in the sense that we're used to. The multiplication satisfies the Leibniz rule. It's all the things that I want because basically the filtration's jumping in the way that I hope it does. Okay. Yes. Okay. So now I want to generalize this in sort of 2 directions. The first is to generalize it to look at just the equivariants. And then the second part is going to be to generalize, to answer sort of what do I mean by various twisted products. And it'll actually be a little easier to satisfy the second condition first. So what do I mean by twisted products? And Birgit essentially set the stage for this, and then we've seen sort of several talks subsequently involving this. I want to have, say, a commutative multiplication from R smash R back to R. But then I also want to have sort of some collection of twisted versions for some pairs of subgroups K inside H, inside G. I want to have maps that look like the norm from K to H of the restriction to K of R back to the restriction to H of R. And these should have nice properties. These should be maps of commutative rings. Now I'm lying here in a very bad way. When I say commutative in both this line and in this one, I mean that I have a coherently commutative multiplication. So I'm drinking the infinity Kool-Aid. I guess there's a lot of it from the way I phrased it. And that's, in the more traditional language, I mean that I have an E-infinity multiplication, where the group is acting on my E-infinity operad trivially. So it's just an ordinary combinatorial E-infinity multiplication, and that's what I have here, and then I ask that I have these. And as having this kind of structure, it puts in a lot of compatibility conditions. So, oops. Oh, I'll call this a norm map. This is going to be my twisted product. Which I'll also usually slip up and call norms. So having one for the pair k into h gives me a lot of compatibility. So if we have a norm for k inside h, then maybe I'll write it as k to h to remind myself that I have this norm. Then for any subgroup J sitting inside H, we get a bunch of things. We get one that looks like K intersect J has a norm up to J. And for any G in G, we also get that GK, G inverse, transfers up to G, H, G inverse. And finally, I want to have a compatibility condition. So also want all that infinity Kool-Aid apparently made me strong. We want some compatibility conditions. Namely, let's say I had a triple of subgroups, H, K inside H inside, I don't know, L. And I had transfers for each of these, K to H and H to L. Then I had my norm from K to H of the restriction to K of R. This went up to the restriction to H of R. That was part of the data that I was specifying basically by this symbol. And then I could take and apply the norm from H to L to this whole diagram. And this is the norm is a functor, so I can, it's a symmetric monoidal functor, so it preserves these E-infinity monoids. And I can further compose now with the norm from H to L. And I can recognize the source. Well, the source is the norm from K to L of IK upper star R. And I see that this is giving me my norm from K all the way up to L. and this is kind of my compatibility, that when I have an intermediate subgroup where I have all the possible norms between them, then I can norm and compose, and I get the right answer. So Birgit talked about this. When she talked about the G-commutative monoids. Namely, I have these operations where I have an extension of my multiplication over not just sets, which is what I'm guaranteed by just the E infinity part, but over finite G sets. And I can ask for less. I can ask for now extensions just over some collections of things. And so Andrew Blumberg and I described this structure. Oops. And this is sort of the basic setup. So let me say, I'll make a definition to sort of turn this more into math. So I'll make 3 equivalent definitions. So an indexing system and the indexing here is that it's indexing twisted multiplications is a collection of full subcategories of finite H sets as H ranges over all of the subgroups of G. And my collection, I have one for each H, and it satisfies a few conditions. First, O of H is closed under disjoint unions and finite limits. Second, well, O of H sits inside fin H. And if K sits inside H, well, really I could just do if K is subconjugate to H, then I have a restriction that takes me from finite H sets down to finite K sets. Oops, K, upper star. And OK sits inside here. So my second condition is that when I do this composite, I actually land in OK. So my restriction of one of these things is, again, one of these things. So if you're following along at your seat, 1 is not quite 1. 1 and 2 together are basically giving me that I have a collection of finite sets. Closure under finite limits means I contain the terminal object point. And closure under disjoint union means I contain arbitrary finite disjoint unions of points. And I'm a full subcategory, so I get any way to sort of take a finite collection of points to a finite collection of points. And that was the sort of Siegel model of an E infinity monoid. I have an extension of the Cartesian product over all finite sets. So that's part 1. And then this closure under restriction, well, that's the condition up there, that if I had norms for something, then I restrict down to subgroups. Well, I break that up into its orbits, and I see all the pieces. The last one, that I have this compatibility under composition, is my third condition here, and that is if H mod K is in O of H, then when I look at induction from fin K back up to fin H, Well, again, O of k sits inside here. O of h sits inside here. And I ask that the image of induction land here. Or put another way, inducing up something in O of k lands in O of h. I don't ask for this in general. So here's an example. That's the end of my definition. So maybe several examples. First, take O of h to be fin h. The three axioms are pretty easy to verify here. There's not a lot to do. OK, so exercise. Second, take O of h to be just sets with a trivial action. So write it as fin sitting inside fin h as sets with trivial action. OK, so if I have first, I'm taking the full subcategory for this, so that part's fine. I have one for each of these. Finite sets are closed under disjoint union. They're closed under limits. In this case, the only thing I have to check is it closed under sub-objects and products? And if I have things with a trivial action, any sub-object has a trivial action. Any product of them has a trivial action. The restriction of something with a trivial action still has a trivial action. I don't magically endow it with something. And then this condition is vacuous. The only time I have h mod k having a trivial action is if h equals k. And the induction from h to itself is the identity. So that actually works pretty well for most things. So that works. And maybe a non-trivial one. I'm going to take O of h to be just finite sets if h is all of g, and to be fin h if h is a proper subgroup of g. So in this case, I have no transfers up to g itself, but I have everything that shows up below. And again, it's not hard to check the conditions. The only one that ever ends up being something to often think about is the induction condition, but then I'd never induce up to g, so I don't ever have to worry about that here. OK, I said I was going to give 3 definitions for this. That was one. And the 3 sort of slightly different features. The third is actually going to let me draw pictures more easily. Oops. All right, number 2. So number 2 is sort of simpler to state. So definition the second. An indexing subcategory is a wide subcategory of finite G sets that is finite coproduct complete and pullback stable. Okay, so what do the various adjectives mean? So wide, this means contains all the objects. Sometimes people call this luff, which is full spelled backwards. Anyway, finite coproduct complete. Well, this means that I can form my finite coproducts here. Finite G-sets has all finite coproducts. And I'm asking that if I form the finite coproduct of some collection of objects, then it's still in here. Well, what do I mean by this? Because I said that I'm containing all the objects. So, like, of course, the things are, this is really a statement about the maps. That I have fold maps between objects. I can take the disjoint union of maps in this. I have the empty set mapping to any object as sort of the initial thing. And those collections together, that's what finite coproduct complete means. And pullback stable, well, this means that if I have S goes to T, and this is in my category C, and then I have an arbitrary map here. This is just a map of finite G-sets. Then I can form the pullback. And pullback stability means that this is actually also in C, that I can pull back along arbitrary morphisms in the big category. It's not saying that it's closed under pullbacks by itself. It's a stronger condition. I can pull back along arbitrary morphisms in the category. So I like this one because I was thinking the whole time, I want to be able to also talk about motivic cases. And motivic cases behave a lot more like a compact Lie group. And I mean, finite groups are compact Lie groups, but it turns out there are compact Lie groups that are not finite groups. This is like a perpetual source of difficulty in my life. Mainly because everyone asks me, well, what happens for compact Lie groups that are not finite? But the issue that shows up there is, of course, I have like things that are bigger than zero-dimensional. So all of my usual formulas describing Mackey conditions, like transfers and restrictions, they get shifted by the degree. And then I stop being able to understand it because I'm secretly an algebraist at heart. It's just that no one believes me when I say that. And I know, respect people when they tell you their identity. So I can make that joke. So they have this, when I'm doing the motivic setting, I don't quite know how exactly to describe this first condition, namely a collection of subcategories. The second one, I can do lots of ways, sort of varying the context, and that's what I might want to do. Instead of finite G-sets, I might do something like smooth schemes over K and étale maps between them. That's sort of giving me an analog of this. And in fact, in the compact Lie case, I could do something similar where I'm looking at like finite G-sets or finite maps between various G-set type things. And if I do that, then I can make this exact same definition in say, motivic or in a lot of the other contexts, or really anything. If I was doing sort of the Barwick school, their vast generalization of equivariant homotopy theory, I can do this for their epiorbital context, anything like that. So I wanted to make sure to include this because it's the easiest to generalize. But then it's not the most convenient to work with. In fact, neither of these is. So that's why I'm going to do definition the third. And this one is due to independently to John Rubin and Beltran, Barnes, and Reutzheim. And when I get back, I'll add that these were due to Andrew and me. So they define the following. So a transfer system is a weak subposet of the poset of subgroups of G. that's closed that contains all the objects. And satisfies three conditions. Well, the first I'll say what weak means. Weak means that, I'll use an arrow to note my partial order, just like I was doing, I guess, on this board, and I erased it. So if H goes to K, then I know that H is actually a subgroup of K. I have a conjugation condition. If H goes to K, and G is in G, GH, G inverse, goes to GK, G inverse. And the last is, whoops. Come on. And the last is the restriction type condition. If H goes to K, and J is an arbitrary subgroup of K, then H intersect J goes to J. So if I hadn't erased that board to write this, you would have seen that I wrote the same three things that I had written originally. I'd say this is evidence that I wasn't extemporizing, but in fact it was pure chance that the timing worked out. But I did choose the notation on the earlier board to indicate, like, I'm thinking of I have norms or transfers that go from H to K. And these are the three conditions that are encoded. So I said I've given three definitions. In fact, these three definitions are all equivalent. And so just choose whichever one you want. The last one, these transfer systems, this is a combinatorial object that sits inside this poset of finite of subgroups of G. Something that I can probably work with pretty easily. So while I'm erasing, any questions?
Maybe I missed it. Could you say what weak means?
Weak is condition 1.
Oh, okay. Can you indicate the equivalences go?
Pardon?
Are the three equivalences they work?
Yeah. So when I look at the category of finite G-sets, if I look at the various comma categories, the categories over an orbit G mod H, then the category of finite G-sets over G mod H, that's equivalent to the category of finite H-sets. So what I do is I look inside that comma category at the full subcategory of things that map to to G mod H. So I look inside my wide subcategory of fin G, and I look at all the things that map to G mod H. And I unpack that. That's equivalent to a full subcategory of finite H sets. That was my O of H. So that's the direction from 2 to 1. The direction from 1 to 2 is I say that a map is in my wide subcategory if, when I break it up into a disjoint union of orbits, I make a statement about the stabilizers, which is exactly what I wrote down in these secretly. And then for the getting between these, it's understanding that, well, this one is in some ways the most transparently connected to this one. You take your transfer system, anytime you have a transfer H to K, you put in the orbit K mod H, and then you close this up under, you take the finite coproduct completion, basically, of those. So, other questions? Because I've got more to erase. Oh, yeah, thank you. So I went one time to what I'd always called Bergen, but then that was wrong. That was the first thing I learned, literally in the car when Bjørn came and picked me up at the airport. And there's a vowel that's actually used that makes it closer to bargain, but I can't say. So I'm going to just imagine that I knew how to say the name of the place. And Bjørn said to me, you've got to go try this one restaurant and eat reindeer. and I thought, I can't eat Rudolph. I was scandalized, and I was even more scandalized by how tender and only lightly gamey, in fact, the reindeer was. So thank you for a better culinary suggestion than just shoot the oil. Still traumatized. Thank you, Tom. That is what I wanted to say. Okay. All right. So how do I tie this back? Well, the main result here is a theorem that's due to a lot of people. So I'll just start putting names. Andrew and I proved part of this. And then Bonventre Pereira. Oops. Gutierrez White. And John Rubin. And the result is that I have a poset of indexing systems. Or equivalently a poset of any of the others. And the poset structure is either further refinement in the transfer system. It's just inclusion. If I have these wide subcategories, they sit inside each other. That's a poset. And the result, that's the target of a functor. And the source is the homotopy category of what we call n-infinity operads. And this is an equivalence of categories. So these are sort of equivariant generalizations of E infinity that encode some norms. And then the assignment is to your n-infinity operad, take the collection of norms that n-infinity operad encodes. And this is the equivalence. This direction is the easy direction. This is the one that Andrew and I did, where you basically can say, okay, well, the work of a lot of people in the 70s through the 90s described for us how to really understand E-infinity operads and the homotopy category of operads. And we can just copy all their shit. And I forgot that I said that I could be recorded. We just copy all of their incredible work. And could you, edit that for me? Okay, thank you. We can't. Well, sure, can't. We just copy their arguments, and that produces, first, that this is actually essentially discrete, that it's a poset, and then the inclusion part is pretty straightforward. And then the hard part... I mean, sure, I could also say that. Yeah. Yeah, because, they're, in a strong way, they're discrete. Yeah, thank you. Yeah. Yeah. I've only drunk some of the Kool-Aid, Thomas, and I was hoping that you wouldn't point that out. I'm not yet a true believer. So that also needs to be edited out, just as an aside. You know, Tina, you might be right. There might be more extemporizing than I was willing to admit earlier. Okay, so this is sort of the context. And, all right, I've got plenty of time, more than enough to say what I need. So these are the twisted multiplications that I want to understand. And I want to sort of build a filtration that records this, or better matches this. So first, let me say what goes wrong. So, okay, this is the last part. Filtrations. So I yell at introduce for us, and I apologize, I forgot the notation you used, but the free operatic algebra functor on some spectrum. So let me say I've got some M, and M is going to be now a G-spectrum. And this, it might be the commutative, the free commutative monoid on it, but really I could also put in any old O for an operatic algebra O, and this is going to be, well, it's going to be an infinity operad. And so I have something that looks like the usual decomposition of this into symmetric powers. I have the 0th symmetric power, and then I have the 1st symmetric power, and then I have the 2nd symmetric power. And I don't know, there are no groups bigger than C2, so this is as far as I need to go anyway. Now, when I'm doing this, I start to run into questions, and this is tied into actually the stability stuff that Ayelet was talking about. I might want to understand what's the connectivity of this, or what happens as I start to compute, as I suspend M and then take loops, which has the effect of just shifting this back down in algebra. So when I start to suspend M, in fact, I just want to answer the following much more basic question. If M is K connected, or connective, then what does that say for each of the pieces? What is the connectivity of these symmetric powers? Well, the first one I know the connectivity of. That's great. The second one, M, I also know the connectivity of. Because I'm able to say, if I assume something, then I get to assume that something. Now it gets weird. Okay. And the weird part comes from the fact that any time some index of a pair of subgroups divides n, then I deform the connectivity. Oops. So what do I mean? And what do I mean by the connectivity here? So my connectivity, well, on the one hand, it means I can build my spectrum out of the K-sphere via various homotopy colimits. And the what and the various here is actually doing a lot of work, because I could say, well, I'm letting the group act on things, or I could say that I can build the spectrum out of G mod H plus smash the K-sphere via less exotic homotopy colimits. But I mean the same thing essentially in both. So whichever you're more comfortable with, take that as your definition of connective. And I can check this kind of connectivity using the geometric fixed points, the sort of functor that Emanuele talked about, which is nice because this also plays nicely with the symmetric monoidal structure. So this is the same statement as the connectivity, the ordinary connectivity of the H geometric fixed points of my spectrum is at least k for all subgroups inside G. So I can detect there's a yeah. The ordinary connectiveness versus connectivity. Maybe that's what I want to say. Yeah, I feel like as a community we need to come together and like say that at some point in the distant past there was a choice that was made and we no longer make that choice. Namely this -1. But yes, thank you, I did. Okay, so I can detect all of this with the geometric fixed points, but now I start to run into a problem. So here's my further example. If G is the sixth group of order 2, well, first, what are the possible transfer systems? Well, I have 2 indexing systems. And I can write them using, to completely blur the distinction, the language of indexing subcategories, finite, like just all finite sets inside finite G. Oh, that's a terrible way to say this. No, I won't do that. I'll draw my picture. This is the subgroup lattice of C2. The trivial group sits inside C2. There's only one option that I can do. Do I have that? There's a choice. That's what I meant. Do I have the arrow or not? Those are the 2 indexing systems. So the first one is the thing that gives me just naive E infinity things. The second gives me the genuine commutative or GE infinity things. And when I have this one, when I have the arrow, so in the genuine case, then we have sitting inside O2 plus smash over sigma 2 m smash squared, we have a copy of the norm, which also looks like the smash square, but I'm doing a different group action. And so when I take the geometric fixed points, well, sitting inside here, and this is something that Emanuele talked about, that when I'm looking at the norm and I take the geometric fixed points, the geometric fixed points undoes the norm. So this is just m. Well, I forget down. And so when I look at the connectivity of that second piece, so if m is k connective, so is this O2 plus smash over sigma 2 m smash square. So when I try to do things like Andre Quillen cohomology, it breaks down immediately. Remember at the very start I talked about the Whitehead tower and how the connectivity of the products in the Whitehead tower grew in the expected way. This is saying that fails for the norms, that the connectivity of the norm of something is the same as the connectivity of that something, because the norm sort of contains a weird skew diagonal copy of that something, and the rest of the stuff is kind of free away from that skew diagonal copy. So this tells me when I'm trying to approximate things and do some kind of Andre Quillen-y, I'll get it eventually, Andre Quillen-y type construction, I can't just do something with this ordinary connectivity. And so in the last few minutes, I'll build my generalized filtrations. So I'm going to say if O is an indexing system, and now I feel empowered to say that, which is the same thing as an n-infinity operad, thank you, which is the same thing as a transfer system, which is the same as an indexing category, so whatever you want to think of. But I'm going to do the discrete one. If it's an indexing system, then for each n at least 0, let tau bigger than or equal to n O be, and I'll write the symbols first, it's the localizing subcategory generated by G plus smash over H with now a representation sphere. And it's the representation sphere associated to a permutation representation on T, where T, I'm just going to have some backup, where T is an admissible H set, so T is an O of H, and the cardinality of T is at least N. And so what do all the symbols mean? This means the permutation representation. If you give me a finite H set, then I take the vector space whose basis is that finite H set and let the group act by permuting the basis vectors. This part means the localizing subcategory. So in other words, I close up under HOCO-limbs and extensions. So if I have a cofiber sequence where the outer two pieces are in my category, the middle one also is. So this is the algebra used. I'm not closing up under fibers. So these are not triangulated. And this is like a big distinction. Okay, so essentially by construction, this is really well adapted for multiplications parameterized by O. So first, notice that tau be equal to n O. This contains tau bigger than or equal to n plus 1 O. And so if I take and let p upper n minus 1 O be the nullification, killing tau big equal to NO, then I have a natural transformation, PNO maps to P n minus 1O, which heuristically is if I form something where I kill off a bunch of stuff and then I kill off more stuff, that's the result of killing off all of the stuff. It's a very brutal procedure. And second, this collection, this is my version of the Postnikov tower, but I have one of these for any now indexing system. And second, it's a filtered category. So this is the assignment, n goes to tau being equal to n. O is a filtered category. And in fact, this filtered object is an O algebra in filtered categories. And in fact, I can say even more. In fact, it's the O algebra in filtered localizing categories. Generated by S1 infiltration 1. So there's a sense in which it's universal. But this is all I needed. Remember, the key property of, say, the Whitehead tower instead of the Postnikov tower was that when I used the Whitehead tower, the product of something in filtration K with something in filtration L was infiltration K plus L. This is built to have the same property. So I can spell it out as, if I do tau big and equal to K, and I smash it with tau big and equal to L, this sits inside tau big and equal to K plus L. And in fact, if H mod K is in O of H, then the norm from K to H of the version of this for K, this sits inside tau being equal to K times the index of H and K. So everything that I was complaining about, that I said the connectivity fails, that it doesn't do the right things in the Postnikov case, I've built a new filtration that filters away all of the higher twisted products in exactly the way that I would hope. And I've done it in sort of the minimal amount of data, namely it's exactly what O recorded. Now there's one thing that I want to end with, and I have no time, so I should have told fewer stories. I don't regret it, Tom. Thank you. I appreciate that. Okay, the first is the theorem of Balchin, Barnes, and Reutzheim. And I love this result, so I'm excited to get to state it. And that is, there are cat n plus 1, which is something like 1 over 2n plus 1 times 2n plus 1, choose n, transfer systems for Cp to the n. This grows fast. I don't know, in homotopy theory, we're not used to factorials, especially, well, we are if we like, oh, no, this just means you're taking the homotopy orbits. That's the only time we're used to factorials. This is like the actual, this is the number, and this grows fast. In contrast, so maybe like a counterpoint. Many of the tau big and equal to something O's randomly agree. By which I mean there are only 2 to the n of these. So when I think about these, randomly, that's not a real word. I mean, randomly, it's predictable, so that's the exact opposite of random. But it's maybe I should have said unexpected collisions, that you have a lot of these things a priori I'd have the same number, but in fact, many, many of them collapse down to give you the exact same thing. So there's sort of more structure in the O algebras and index systems than we had anticipated. All right, I'll stop there. Thank you.
Thank you, Mike. Other questions?
Can you say something about the convergence of these new filtrations?
Oh, yeah. Strong convergence on connective things, like anything, sort of the nicest possible setup. In fact, you can do better. You can, as I vary O instead of varying N, I can vary O in the post set. And if O prime is bigger than O, then to form the nullification for O prime, I killed off things for the one for O. So I get a natural transformation that respects N. So I get a map of towers Pn of O to Pn of O prime. But I can weirdly go backwards at the cost of decreasing N. So in fact, all of these can be viewed as sitting between the slice, or the ordinary Postnikov towers run at different speeds. And since the Postnikov tower converges really well, all these do too. Yeah?
Do you know anything about the categories of slices?
No. Yeah, I'd love to. At one extreme, well, there's two extremes where I can say something. There's the one extreme where I took the initial indexing system, the one where I have no transfers between anything. That corresponds to the Postnikov truncations, the ordinary Postnikov truncations. There I can. Those are the categories of Mackey functors. And that one happens to be a T structure. And so I get the relative fibers are always in the same abelian category. Otherwise, they're basically never T structures from that point on. And I don't know. For some of them, you can say things about you can sort of identify, the bottom piece is actually always Mackey functors. The next one you can also sometimes identify. But I don't have a good description. That's a great question.
Isn't this a case of cellularity that can be made much more general?
Yeah. Sort of secretly underlying this, I really had a kind of diagram category that I was thinking of indexing over. And yes, anything that I'm building in that way, I could get it. So thank you. So if I were thinking in motivic homotopy, I'd even made the time to be like, oh, and I can do the indexing categories in the motivic context. I could do the same thing that I did here and build various things that are going to control the same parts that I would see. As Tom reminded me yesterday, that's not quite controlling the same thing as normed motivic spectra, because there I have transfers along arbitrary maps of smooth schemes. But it's controlling sub-pieces of étale.
Just a quick clarification to your answer to the last one. You said almost never T structures. Is there an example of a non-trivial, like a non-initial indexing category where you're already getting a T structure?
I think almost never means the initial one is the only example. Because basically what goes wrong is the fact that it's not initial means at some point I'm going to pick up an H set that's not trivial for some H. The moment I switch from the one to the other, the next category is not just the suspension of the previous one. So I should say all of these do assemble. There is a T structure for each of these. It's not the filtration associated to a T structure, is what I should have said.
Does suspension have to be the thing that moves you from the T structure to the other functor?
I think so. I've never thought of the other things. I don't actually even have sort of a functor that's an equivalence between each and the next in general.
Two questions. So you said those don't have limits, right?
Right.
Finite limits?
It doesn't even have fibers.
Okay, the other question. Do you have like a translation, because you said you wanted the motivic things, a translation of the post set and operads into the motivic set?
I don't know. Tom, is there a translation for the things that I said? Okay.
How did I know?
I don't know. I'd love to know that.
More questions?
I want to ask a question. So is the story much easier if you work over Z instead of split?
If I work over Z,
Somehow spectral Mackey functors or Calais-derived Mackey functors.
so there's an issue with the norms in Calayden's derived Mackey functors. That Calayden's derived Mackey functors, this is like, who showed this? Korea. I'm blanking on the other names, and I apologize if you're here in the audience, shout and embarrass me publicly in front of everyone. But Calayden's derived category Mackey functors is the same as modules over the push forward from the trivial group to G of HZ. Or if you prefer, this is the same thing as you take, you look at sort of the spectral Mackey functor where I assign the value HZ to the slots, and I have a space of maps between them. This isn't a G E infinity ring. So its category of modules doesn't inherit the structure of a G symmetric monoidal category. It's essentially like Tanaka duality tells me that. So no, I can't do that. But if I work in just actual Mackey functors, so I hit the Homs with pi 0, then the whole story does become a little more transparent, but I also don't worry about the shifts. I can do this for DG Mackey functors, but DG in the algebraic sense, not in the Kaleidynic sense. And then I can tell the same story.